Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 34 on volume and dimension.
We've computed the areas of two-dimensional shapes and the volumes of three-dimensional shapes. What do you think comes next? The fourth dimension? The fifth dimension? In this lesson, we're going to do them all at once.
We begin our lesson with that timeless question. What is the fourth dimension? Well, that sounds kind of spooky. We're going to jack it up a level and answer the question, what is the nth dimension? But we're going to start at the beginning. Let's say n equals 1. What is that? Well, that's simply the real number line that you all know and love. We could coordinatize it by some variable, x. When we move up to the second dimension, well, now we have two variables to state where we are on the coordinate plane. Call it x and y. 3 dimensions is a little bit harder to draw, but no less difficult to understand. We have x, y, and z. But now, when we get to the fourth dimension, it's a little difficult to draw pictures. We can, however, simply add another coordinate. You might be tempted to use t for time or some other variable name, but why don't we just use subscripts? x1, x2, x3, x4. The reason for this being that when we move to the nth dimension, well, for large values of n, we don't have enough letters, but we do have enough subscripts. Now, drawing pictures in the nth dimension is hard. Therefore, we're going to proceed by exploring through volumes and shapes. 3 simple shapes in particular: cubes, simplices, which are analogs of triangles or pyramids, and balls. Now, what do we mean when we say volume in high dimensions? Well, let's take a moment and think about that. As dimension of a object goes from 0 to n, we know what 3-dimensional volume means. That's simply volume. But we also know what 2-dimensional volume means. That is area. What is 1-dimensional volume? Well, that is really length. Okay, you've got those 3 down. What is 0-dimensional volume? Well, a 0-dimensional object is simply a collection of points. How many points? That is the volume. 0-dimensional volume is counting. And now, with these in place, we can move to n-dimensional volume, which we will call hypervolume if we're feeling epic, or we might just simply call n-volume. That will work. Let's build our intuition for n-dimensional volume by looking at an n-dimensional cube. This is going to be a cube where all of the sides have unit length. So in dimension 3, it's the familiar object. What is a 2-dimensional cube? It's simply a square with side lengths 1. What is a 1-dimensional cube? Well, it's got to be some interval, an interval of length 1. What's a 0-dimensional cube? It's a 0-dimensional set whose volume, or count, is equal to 1. It's just a simple point. And from that, we can extrapolate to higher dimensional cubes. But at this point, pictures fail, and we need to translate to equations. Therefore, we'll define the unit n-dimensional cube as those points in n-dimensional space whose coordinates, x sub I, satisfy the inequalities x sub I bigger than or equal to 0 and less than or equal to 1 for all I. Now, how do you visualize that? Well, it's hard to do with your eyes, but you can do it with your hands. If you think of each coordinate as an independent parameter, then it is remarkably similar to what happens when you slide an equalizer or slider bars up and down. Perhaps you've played with something like this on a sound system. Each of those slider bars is like a coordinate in the n-dimensional cube, where n is the number of slider bars. Each can go up or down, independent of the other, until you hit the boundary, where it has to stop. Now, with that in mind, let's take a look at volumes. As we consider what happens in each dimension, how do we get from one cube to the next? At each stage, what we're doing is taking the lower dimensional cube and then crossing it with an interval, making a one-parameter family of such objects. Now, in every case, the volume is 1. We're used to that in area, length times width, or in 3D volume, length times width times height. In each case, it's 1 times 1 times 1. In fact, this is really the basis for how you should think about n-dimensional volume. The surface area, well, that's a little bit harder to wrap your brain around, but we want to look at the boundary of the cube and say how much n minus 1 dimensional volume is there. So if we take a one-dimensional interval and say, what's the zero-dimensional volume of the boundary? That is, how many points on the boundary? Well, simply 2. Surface area for a two-dimensional object is what we used to call perimeter. And in the case of a square, the perimeter is 4. There are 4 unit edges. Of course, the surface area for a three-dimensional cube is what? Well, you look at each of the 6 faces and compute its unit area. Adding together gives 6. Now, in general, one could argue correctly that the surface area of the n-dimensional cube is in fact 2n, the number of boundary faces that you have. And that pattern works all the way down, even to dimension 0. The diagonal of a cube is the distance between opposite corners. We know from Pythagoras what that is for a two-dimensional cube. That's square root of 2. What about for a three-dimensional cube? Well, we would have to apply the Pythagorean theorem twice to obtain the square root of 3 as the length of this long diagonal between opposite corners. If we continue inductively, we can show that the diagonal of the n-dimensional cube has length square root of n. That's a little crazy, because for large values of n, you can have a very, very small unit cube such that the opposite corners are very, very far apart. That's a little strange. But this pattern continues down, even to dimensions 1 and 0. Lastly, if we count the number of corners in an n-dimensional cube, we see for a square, there's 4. For a cube, there is 8. And in general, it's not hard to show that there are 2 to the n corners. Let's move on to a different shape, one that requires some calculus to understand. This is the simplex. This is an n-dimensional generalization of a triangle or a pyramid. The unit simplex is defined algebraically as a subset of the unit cube that satisfies an additional constraint. This being that the sum of the coordinates is less than or equal to 1. Well, what does that mean in terms of our slider bar analogy? This means that you can take any of the individual bars and slide it all the way up to 1. However, you can't do this independently. If you want to move the other slider bars up, you have to do so in a way that the sum of the values does not exceed the threshold of 1. That means that this is a highly constrained set. It's not a large subset of the n-dimensional cube. It feels much smaller. We expect to see that reflected in the volume. Let's see how that works. First, let's explore a few properties, and then we'll compute the n-dimensional volume. The number of corners of an n-dimensional simplex is much less than that of a cube. The n-dimensional simplex has n plus 1 corners. What is the volume? Well, we know for a single simplex it's just a point. The number of points is 1. We know for a one-dimensional simplex, since it's the same as a one-dimensional cube, we just get a length of 1. Now, a triangle, as we all know, gives us area 1/2. When we look at a three-dimensional simplex, it's a cone over that triangle. We know the volume of a cone is going to be 1/3. The height, 1, times the area of the base, 1/2. Now, we start to see a little bit of a pattern here. What if I told you that the four-dimensional simplex had four-dimensional volume equal to 1/24? That's true. And knowing that, you would be convinced of the pattern, namely that the volume of the n-dimensional simplex, v sub n, must be 1 over n factorial. Now, that's a good guess. Let's see if we can show it.